All right, so this is the second video for Unit 6 covering the second part of Chapter 14. So Section 3 covers really looking at simple harmonic motion. So we talked a little bit about the sinusoidal function beforehand. So if we look at this spring, it's going to undergo simple harmonic motion. The resting position is your 0. It's been squished here, and then it oscillates up and down and up and down and up and down. When we go to the position versus time graph, we get this sinusoidal function right here. Okay. Now, if we look at, because we know the position versus time graph, we can actually we can find the the velocity versus time graph and the acceleration versus time graph. If you look at the graphs, you should notice that they're just shifted over. Okay. They're shifted over essentially a quarter of a wave. So the position graph starts with a crest, the top part of a wave. The velocity versus time graph, it just shifts this whole graph over a quarter of a wave to get there. The acceleration does the exact same thing. It shifts the graph over another quarter of a wave, another quarter of an oscillation. Okay. So as it says here, so you let it go. At the very top, the velocity is 0, but the acceleration is negative because it's going downward. So the mass is now moving down as the velocity is negative. And as the mass nears equilibrium, the restoring force, and then the acceleration decreases. Okay, so as it hits here, the acceleration decreases. And as the time of the pass is moving downward with its maximum speed, okay, it's at the equilibrium position, so the net force is 0. So if there's net force is 0, there's no acceleration. But it has its maximum downward velocity at that point. And then it goes down. As it goes down, it starts to pick up speed again. Wait, sorry, my bad. As it goes down in position, it's going to slow down. So it reaches its maximum velocity at its equilibrium positions, where the forces are balanced. And then at the bottom here, when it gets to the bottom, it stops momentarily. Because at this point it's going downward, slowing down. Here it stops. And then it starts to go back up and speeds up to this point, which is the equilibrium position. And from there, then the spring force is not much at that point, and then it's going to slow down until this point. Let me show you a simulation. So if you watch this, we take this kind of in slow motion here. So you have our velocity and acceleration graphs. And they constantly change. Okay, at this point, our velocity is big, our acceleration is almost non-existent. As it goes up, notice the velocity is increasing up until it hits that equilibrium position. Now it's going to decrease. Okay, it's going to oscillate back and forth. I'm going to send you the link for this simulation and you can play with it as well. Okay. So velocity is negative going down. All right. The mass has reached the lowest position in the motion, which is right here. And that's a turning point. The spring is at its maximum extension, so the net force is upward and the acceleration is positive. So the mass has begun moving upward, the velocity and acceleration are positive because it's going up. And then the mass spring passes through the equilibrium position, so now we're here. Okay, so it has a positive velocity because it's going upward. At that point, there is no net force because the forces are balanced, so the acceleration is 0 at the equilibrium position, which is what shows here. So the velocity is speeding up to that point right here. And then it starts to slow down from this point up. So it's slowing down here, which means you're going to have a negative acceleration. And then it'll just repeat the cycle over and over and over again. And these graphs would look exactly the same for every cycle. And if you go from this point to this point, that's one complete cycle. That's the period of this pendulum, or the spring. And so as this would be the period as well. And this would be the period in acceleration. All right, so the position versus time graph for that motion is x equals a cosine 2 pi little t over big T. Okay, where t indicates the position as a function of time. And then the cosine function can be written in terms of frequency as well. So because frequency is 1 over the period, it's a cosine 2 pi times the frequency times your time. This is at any given time. Little t is your given time period. Big T is your period. So big T is always set for a spring. Little t is where are we in our time period. So kind of to go back to here, big T would be the time it takes to complete a period. Okay. Little t could be any time period along this to figure out where we are for our position versus time graph. This one is given to you on your formula sheet, and it could possibly show up on the AP exam. Velocity graph is an upside down sine function with the same period. So the formula is negative V max, maximum velocity, times the sine of that 2 pi t over period. All right, we have little t over, we have their time divided by our period, so that's the frequency again. And the restoring force causes an acceleration, according to Newton's second law. Acceleration is force divided by mass. Force times distance divided by mass. So we have our spring constant divided by our mass times our displacement. This little x is just the x direction of the force. So ax is equal to force net in the x direction divided by mass. Force is spring constant times your distance, your displacement. Spring constant divided by mass times displacement then is your acceleration for your springs. I know this is a lot of math. You're going to get a chance to practice this. And then the acceleration versus time graph is written that way. The only formulas you're going to have to worry about are the ones on your formula sheet. But I would know if you see a graph like this, you should be able to shift the graph either way depending on what you have. So if you have the velocity versus time graph, you should be able to slide it over a quarter of a wave to get position to the right, slide it over a quarter of a wave to the left to get acceleration versus time. You should know how to do that. All right, so this is just giving you where things are. So at certain points you have A is positive and A is negative at other points. Okay. So we have a track ladder oscillates horizontally on a spring at a frequency of a half a hertz. So it makes a half an oscillation per second. So it makes one complete cycle in 2 seconds then, just like it shows on the right. Suppose the glider is pulled to the right of its equilibrium position by 12 centimeters and then released. Where will it be? Where will the glider be after 1 second after its release? And what is its velocity at that point? All right. So So the glider undergoes simple harmonic motion with an amplitude of 12 centimeters. The frequency is half a hertz. So the period is 1/2 hertz or 2 seconds. The glider is released at a maximum extension from the equilibrium position, meaning that we can take that point, that 12-second point, to be time is 0. And you could create a graph that looks like this. So 1 second is exactly half of the period, as the graph of the motion and figure to the right shows. So half a cycle brings the glider to its left turning point. So half a period would get it halfway through its motion. And so, like it says here, drawing a graph was an important step that helped make the sense of this motion. Because if you know its period, which if you know its frequency, period is 1/2 frequency, you can figure out the graph is going to essentially look like this. And if you know the amplitude, how far it gets stretched, at a half a period, it's going to be the opposite displacement. All right, so a 500 gram block is attached to a spring on a horizontal surface. The block is pulled to stretch the spring by 10 centimeters, then gently released. A short time later, as the block passes through the equilibrium position, its speed is 1 meter per second. So we're going to figure out the block's period of oscillation and the block's speed at the point where the spring is compressed by 5 centimeters. So if we look at this, so the maximum speed is when it passes through the equilibrium position, okay, which is 2FA. The amplitude is 10 centimeters, so which is 0.1 meters. And the speed of that is 1 meter per second. 2 pi f is 10 radians per second. Okay. So we can actually use the period of this oscillation. We can go back here and use this. We know at a certain time, we know what speed, we can solve for that. So I would like you to try to solve this on your own. The answers are 0.63 seconds and 0.84 meters per second. This talks about angular speed. You don't have to worry about the angular speed. You can just use the formulas already given to you beforehand. So obviously we got some connection to circular motion here. So this ball, if it goes in a circle around the turntable, if you just could look at it from a sideways point of view, the ball would look like it's going back and forth, which is like a simple harmonic motion of the spring. So the x component of the circular motion on theta is x equals a cosine theta, like we've done before. The angle at a time later is theta equals wt, and w is the particle's angular velocity, which is 2 pi times your frequency. So the particle's x component is expressed as a cosine 2 frequency times the period, and that's the same equation as the position of a mass on a spring. The velocity is therefore 2 pi f a, where a is the length of your pendulum. Okay. So a in the x component is negative a x theta. So we know our angle. A lot of this you're not necessarily going to need, but it's good just to look at for a review from circular motion. Okay, so I would make sure that you look over this page here and look at these formulas and just at least understand how to do them. There will be some practice with those to make sure that you understand what's going on with them. Okay. If you have a turntable in your microwave, you can look at them. You can look at this and actually it makes the same view. You can look at it sideways. It just looks like it's going back and forth. So you can figure out the period and the frequency of that cup. And that's simple harmonic motion. We're not going to do this sample problem. Yeah, we will. So the big building in Chicago is 100 stories high. Strong winds cause the building to sway. On really windy days, the top of the building oscillates with an amplitude of 40 centimeters and a period of 7.7 seconds. What's the maximum speed and acceleration of the top of the building? All right. So we know so the amplitude is 0.4 meters. That's A. So we know the frequency is 1 over the period. The period is 7.7 seconds, so 1 divided by 7.7 seconds is 0.13 hertz. Really, really low frequency. All right, so we can use one of the equations there to solve for velocity and acceleration. So our acceleration, the maximum acceleration, is 2 pi f squared times your amplitude, which is 0.27 meters per second squared. Maximum velocity is 2 pi frequency times your amplitude again, the maximum swaying distance. So 2 pi times 0.13 hertz times 0.4 meters is 0.33 meters per second. And the acceleration isn't very big, which should be expected. Okay, spring problem here. So the frequency is the square root of spring constant divided by mass again. All right, so we're going to move on to energy. So because it's moving, there's energy involved. So the spring oscillates back and forth. So when it's maximum out, it has its most potential energy. And then it decreases in potential and gains kinetic up until the equilibrium position, where it has the most kinetic energy. At that point, it's going to start slowing down, so the kinetic energy decreases, and your potential energy then is going to increase, because the potential then is for that spring to push it back out. And the same is true with pendulums. If you watch, the total energy remains consistent. It's just that the kinetic and potential switch back and forth. Springs, they do the exact same thing. So for a mass on a spring, you get this the energy graph that looks like this. And they line up the equilibrium positions and the maximum and minimum displacements. So the potential energy of a mass on a spring is U equals 1/2 kx squared. And then the conservation of energy says that the kinetic energy plus the internal energy is equal to your total energy, and that remains constant. Kinetic energy is 1/2 mv squared. That doesn't change no matter where you are. Potential energy of a spring, 1/2 kx squared. We covered that part before. So the kinetic energy plus the internal spring energy is constant. These two get a constant total the whole time. That's why this total spring energy, this E, is a horizontal line at the top there. All right, so at maximum displacement, the energy is total potential. And at equilibrium, it's totally kinetic. And the totals just go back and forth. The totals of each go back and forth, but the sum remains consistent. So because of conservation of energy, the maximum potential energy must be equal to the maximum kinetic energy. So solving for maximum velocity, we can actually rearrange this equation to solve for velocity max is equal to the square root of k times mass divided by the amplitude. So the frequency of simple harmonic motions of masses and springs with are these. So the period of a spring is t equals 2 pi times the square root of m divided by k. M is the mass on the spring, and k is the spring constant. And we get those from these equations right here. So the period and the frequency and period are determined by the physical properties. The frequency and period of a simple harmonic motion does not depend on the amplitude. For springs, it all depends on the spring constant and the mass pulling it. And at the high frequency, you get a stiff spring. Low frequency, you get a really soft spring. It vibrates easily, it oscillates easily. Okay, I'm gonna have you just read this over. All right, so if we have a spring that's unstretched at a length of 10 centimeters, then we add a 25-gram mass to it, and it stretches to 15 centimeters. If the mass is pulled down and released so that it oscillates, what will be the frequency of the oscillation? So this is our situation. Right. So the oscillation frequency depends on the spring constant, which can be determined from the stretch here. And we know that, so we know the mass, so we know the weight, we can figure out the spring constant. Okay, so we know that the spring constant times the stretch is equal to mass times gravity, because the spring constant has to equal, or the spring force from Hooke's law has to equal the weight at the equilibrium position. So the spring constant is mass times gravity. Mass is 25 grams, which is 0.025 kilograms, times your weight, or times acceleration of gravity, 9.8 meters per second squared, divided by how far it stretches. And it stretches 5 centimeters, which is 0.05 meters. So that means our spring constant then is 0.025 times 9.8 divided by 0.05 is 4.9 newtons per meter. So that's your spring constant. That's the stiffness of that spring. Okay, and we can calculate then the oscillation, the frequency. The frequency is 1 over 2 pi times the square root of k over m. Then you solve it and you get a frequency of 2.2 hertz. And you could then, 2.2 hertz is 2.2 oscillations per second. And we could figure out the period on that as well. All right, the last section for this unit. So pendulums have that restoring force that we talked about, where the net force is mass times gravity divided by the length times the arc length that you pull it back. Okay, so the oscillation of the pendulum is a simple harmonic motion. So we know these. Arc length is how far you pull it back times cosine of 2 pi times the frequency times time. Or because the arc length is so small, we can put it in terms of angles as well. So the angle is the angle max times the cosine of 2 pi ft. And we get frequency. The frequency is 1 over 2 pi times g over L. Or period is 2 pi times the square root of L over g. Just reverse everything to get your period equation. Right? I would make sure that you look at these and write them down because you're going to need those as well. And if you notice, the period equation from the pendulums and the springs are very similar. The only thing that changes are these two items here. It's L over G for pendulums. It's mass divided by spring constant for springs. So as for a mass on the spring, the frequency does not depend on the amplitude. Okay, or it doesn't depend on the amplitude, and it's independent of mass. It's all depending on the length and the gravitational field you're in that would cause the acceleration of gravity. So grandfather clock is designed so that one swing of the pendulum is in either direction takes 1 second. What's the length of the pendulum? So one period of the pendulum is 2 swings. So the period then is 2 seconds. So the grandfather clock is designed so one swing of the pendulum in either direction takes 1 second. So it goes in one direction in 1 second. It comes back in the other second. So the period is 2 seconds. So the period then is 1 over the frequency, which is 2 pi times the square root of L over G. Solving for L, we just rearrange it. L is G times T over 2 pi squared. Just kind of so far, hopefully you can see where that rearranging came from. So G is 9.8 meters per second squared. Times T is your 2 seconds is your period. over 2 pi squared gets you your length of about a meter. So just by knowing the period, you can figure out, if you know you're on Earth, so then you know the acceleration due to gravity, you can figure out the length, or vice versa. If you know the length of the pendulum, you can figure out its period, so you can do a test to see if you actually have the correct length. So a pendulum with a tick or tock each second requires a long pendulum of about a meter. So physical pendulum is something that, like a solid object that swings back and forth, that pivots. And that restoring force is actually going to be moving from the center of gravity from that object. So as it gets closer to the bottom, that restoring force decreases, just like I mentioned earlier. So we could look at this in terms of moment of inertia. Okay, think back to the rotational stuff where we talked about moment of inertia. So it's resistance to its change in motion. So if you look at the bottom piece there, the frequency of a physical pendulum, in terms of what we're looking at, let's compare this. So period is 2 pi times the square root of L over G. Now if I go back into this one, L in this case is going to be your moment of inertia. G now is mass times gravity times your distance. Okay. So this is the new formula for frequency of a solid object. Not so like we're talking like a leg, something where the mass of the object is not in, or the string replacement is not insignificant. So a student is on a biometrics lab, measured the length of their leg from hip to heel to be 9.9 meters. What's the frequency of the pendulum motion of the student's leg? What's the period? So we're going to look at the same moment of inertia piece as just mentioned before, and the leg can be considered a rod, which has a moment of inertia of 1/3 meters, mass times the length squared. So the center of the gravity of the uniform leg is at the midpoint, so at your knee, which isn't quite completely accurate, but for this case we'll go with it. So the frequency of a physical pendulum is given by the equation earlier. So before we put in numbers, we'll use the relationships to simplify it. So we know our moment of inertia is 1/3 ml squared. We know the distance where that pivot point is placed is L over half of L. Okay. And if we start simplifying, we see that our L's go away. We see that the L on the top goes away. So in this case, our frequency is 1 over 2 pi squared, or 1 over 2 pi times the square root of 3/2 G over L. Hopefully you can see where we got that. D is the distance from where the center of mass is, that's rotating. And that's half of your length of your object. I is your moment of inertia. We know our moment of inertia is 1/3 ml squared. So we know we can simplify m's and simplify the l's to get this. Okay, so the period and the frequency are thus. Okay, we didn't need to know the mass of the leg to find the period. Doesn't matter. The mass does not matter on this. Okay, so you can do the same thing holding your arms. You can change the moment of inertia by swinging your arms. And that, my friends, is the end of that particular video. I know it's long. I know there's lots of stuff. I would highly recommend for you to make sure you read the textbook as well for this unit and watch the videos. And make sure you ask the questions if you need them. And we'll talk to you soon.